Good morning and good evening from people from America. Thank you for attending. I'm Seungbin Kwon from QISCA, and I am delighted to introduce today's first presenter, Hyungmin Lim. Hyungmin Lim is a senior undergraduate at Yonsei University, majoring in electrical engineering and minoring in physics. His main research interests are in fault-tolerant quantum computing, algorithms, and quantum error correction, and his advisor is Professor Chae-Yin Park. He served as the inaugural president of the Quantum Information Yonsei Academy and is a co-founder of the Quantum Information Science and Computing Association, or QISCA. Then let's welcome Hyungmin Lim to the stage.
Can you hear me?
Yes, we can hear you well.
Okay. I'm gonna start about my presentation. Um, Hello everyone. My name is Hyungmin Lim, and I'm one of the presenter of QISCA and UC Quantum Joint Journal Club. It's an honor to make this chance to me. And today I'm gonna talk about the fixed step Hamiltonian simulation via Cartan decomposition. First, let me introduce myself and but I'm especially interested in FQC algorithms and quantum error corrections, so feel free to contact me. I also referred the original paper published in PRL in 2022 and Penny Lane blog post posted by Corbinian Codman. And these are table of contents, and let's get started. Uh, I'm gonna briefly review the concept of Hamiltonian simulation. And Hamiltonian simulation is the task of simulating time-dependent quantum state. So we should implement time evolution operator efficiently. And if Hamiltonian is time independent, we can express time evolution operator U as exponential of Hamiltonian. And so why Hamiltonian simulation is important? Yeah, maybe in quantum algorithms, many quantum algorithms like quantum phase estimation, variational quantum algorithm, or linear system algorithm for linear systems like HHL, or require Hamiltonian simulation as a subroutine. And high energy physics and also quantum chemistry uses these Hamiltonian simulation algorithms. So I'm going to talk about why quantum computer is important for Hamiltonian simulation, because if I prepare n qubit state, maybe it will require 2 to the n memory to simulate this. And also tensor network has a limitation of Hamiltonian simulation, like MPS or PAPS are also assumed locally entangled states. So I will gonna tell you about prior approaches like trotterization and quantum signal processing. And trotterization is a very simple algorithm for Hamiltonian simulation. It's kind of splitting Hamiltonian to capital N pieces. So we can consider local Hamiltonians, which can express the simulation of M Hamiltonians like Heisenberg model. In Lie algebra, we can find out some properties of metric exponentials like Lie product formula. You can see this. It means if we split this Hamiltonian infinitely, its product converges into original Hamiltonian. So we can consider first term split by n steps and consider error term depends on simulation time t and step n. So we can get error term like t squared divided by large N, and some norms about the commutators. And there are some disadvantages of trotterization because the error term depends on time squared. So it means if you have some bound of error, and if you want to simulate long time, and you should longer your circuit depth, large N, depend on the square of t. So I'm gonna tell you about some theorem about no fast forwarding theorem, um, and published by Andrew Charles. And briefly, it is not possible to simulate a general sparse Hamiltonian for time t using OT. And even pth order trotterization can can't converge to TOT. So what about other Hamiltonians, like Andrew Charles said about a row computable sparse Hamiltonian? But how about other Hamiltonians that we have some other supplementary informations? So there are some fast forwarding approaches. If fast forwarding is it means faster than OT. This thesis is about the fast forwarding Hamiltonian simulation through blob decomposition, but it has very few kind of Hamiltonians. And also our method is trial to fast forwarding Hamiltonian simulation. So I will gonna explain about some key concept of Lie algebra. Maybe you're theoretical physicists. It will be maybe easy, but some students don't know about Lie algebra, so I will explain about that. I'm referred these two books about Brian C. Hall and Humphreys. So let's start about the Baker-Campbell-Hausdorff formula. We can express Hamiltonian as a summation of some local Hamiltonians, which is expressed through a Pauli string. And we want to implement this ut as the exponential of minus iht. And if we think about the matrix exponential, we can get some Baker-Campbell-Hausdorff formula, which is constructed in some commutators and commutators of commutators and infinitely commutator terms. So can we think about some vector space defined additional bilinear map like commutator? So that's the concept of Lie algebra. So a vector space G over field F with an operation G to G, and there are some axioms about Lie algebra. The first one is it should be bilinear map, and second one is the Lie bracket should Lie bracket of itself is 0 about all elements in G. And last one is Jacobi identity, and it implies many important properties of the algebra. So commutator is an example of this Lie bracket. So Lie bracket is the more bigger concept. And using L2 and x plus y, comma x plus y equals 0, we can obtain the anti-commutativity of Lie bracket. And I'm gonna explain about some matrix Lie group. Um, Lie group is more bigger concept, but there are some difficult mathematical definitions like compact or so I don't gonna explain about that. So I will focus on the matrix Lie groups. So um this GL is general linear group. It's about all invertible matrices, and SO is special orthogonal rotations, and SU is special unitary complex rotations, and SP is symplectic transformations. And uh, Lie, actually, matrix Lie group and Lie algebra has very interesting properties. If we exponent the Lie algebra, we can get the matrix Lie group. So we can find the interesting properties of some symmetric groups and Lie algebras. So I will gonna explain about why this property occurs. And I'm gonna explain about two maps in Lie algebra. First one is adjoint map. I'm gonna first explain about the Lie algebra homomorphism and the Lie algebra isomorphism. If you um, if you uh, heard about the abstract algebra, maybe you will know homomorphism. And the homomorphism is some kind of um, map that map that preserves the property of uh, one group to other group. So the algebra homomorphism preserves the property of Lie bracket to one group to other group. And first one is adjoint map. There are two adjoint maps in Lie algebra. First one is defined by the Lie bracket. And so we can express this kind of many kind of commutators like this. We can now write this simply. And I will explain about the adjoint map in the Lie group, like GB matrix Lie group, and with the Lie algebra G. And for each A in G, we can define the linear map, adjoint map, like this matrix products. And we can prove the exponential of adjoint map is adjointment of exponential x. This is my mistake, and it will be very important property when we prove the KAK decomposition, which is the concept of Cartan this Hamiltonian simulation. And this is Lie algebra homomorphisms. If we have some Lie group homomorphism, there exists a unique real linear map, linear map Lie group G to Lie group H, Lie algebra G to Lie algebra H, and these maps are has very interesting properties that preserve the properties of the Lie algebra and Lie group. And so this is why the property occurs I explained. So in a special orthogonal group or special unitary group has some property about determinant one, and in Lie algebra we can see the trace of x is 0, and we can prove that y, if we have a determinant 1, implies the trace of x is 0 in Lie algebra. And these are some compact Lie groups. And so I'm going to explain about how we simulate Hamiltonian via Cartan decomposition. And I will explain this sequences in 3 steps. First, find some Lie subalgebra. This concept it's started by if we have some Hamiltonian, we don't have to care about all the bases in the Hamiltonian algebra. Because Hamiltonian algebra is SU to the n. It's too many bases for one Hamiltonian. So if we have some good Hamiltonian, like two side transfers TFIM, and we can get some Lie algebra, which is generated by this basis in the Hamiltonian. So if we have ZZ and IX and XI as simulation Hamiltonian, we can generate by these Hamiltonians to the Lie group, Lie algebra, like this: IXI, IIX, and IZZ, IYY, IZY, and IYZ. So we don't have to use all spaces of circuits. If we should care about all space of circuits, maybe there are 4 by 4, so 16 base we should care about. And so we can find some, we can see in this graph, we can reduce some dimension of some Hamiltonians by this Lie group. And so in this is TFXI, TFXY, and TFIM and TFXY is dimension is n multiplies to n minus 1, and GXY is n minus 1. So if we should care about the SU2 to the n, maybe we have to think about way more bases in SU2 to the n. But some Hamiltonians like Heisenberg model still have big dimensions. And here is the definition of Cartan decomposition. And Cartan decomposition is just about the group decomposition. And a Lie algebra G is defined as an orthogonal split G, K direct sum, and M. And K is closed by the Lie bracket, but M does not. But M also have good property like Lie bracket of M itself is subgroup of the K, and K and Lie bracket of K and M are in the M. So my question is, how can we find Cartan decomposition? If we find some function named Cartan involutions, we can find a Cartan decomposition easily. Here is definition of Cartan involutions. So a Cartan involution is a map theta G to G satisfying condition below by X, Y in G and all constants in R. And involution satisfies these three properties and linearity and also theta and commutator of xy map to commutator of theta x and theta y, and it's kind of nilpotent, and the theta squared is Ig. And so theta only has eigenvalue plus minus 1 and associated eigenspace G plus minus. And so we can find some Cartan decomposition by Cartan evolutions because the eigenspace G plus and G minus are Cartan decomposition of G. And also we should find named Cartan subalgebra. And Cartan subalgebra satisfies some subalgebra in the M. Because M is not subalgebra because M is not closed by the Lie bracket. So we should find some subalgebra in the M. And we can prove the Cartan subalgebra H is abelian because all commutators in H is in the M and also in the K. So there satisfies just 0. So subalgebra of horizontal space is abelian. And there are some figures you can understand. So if I have some PFI Hamiltonian like this, and we can generate GH by the Cartan Lie bracket, and we can get Cartan decomposition by Cartan involution by G minus G transpose, and we can get the K Lie subalgebra K by ZY and YZ, and also we can get some set ZZYY XI IX. And also we can find some Lie subalgebra, Cartan Lie subalgebra H, Xi, and Ix. And there are another decomposition using this named KAK decomposition. If we have some Cartan decomposition like this and have non-degenerate invariant bilinear form on G, and we get some M, there exists K in the exponential of IK and Lie Cartan subalgebra H in H. So we can Cartan decompose any M in some set. And this implies the unitary decompose like K e to the IHT to K Dagger. And these are the proof of how can we decompose like this. And so how can you find the H and K? If you find K and we then we can find H. And if we get K and H, we can simulate in the arbitrary time t by in fixed depth. So there are theorem in this dissertation, and if we assume a set of coordinates theta in a chart of the Lie group e to the ik, and for Hamiltonian in the M, define the function f like this because we defined the bilinear map before. And so they have, if any local extremum of f theta denoted by theta c, and defining the critical group element kc to k theta c, we have this decomposition. So if we set some v in the Cartan subalgebra H, and we just variationally find the theta that um, that satisfies makes local extremum, and then we find the k we want to decompose because a k looks like this, all product of the Cartan Lie subalgebra. So this is the result of Cartan decomposition. So you can see the way more better result than Trotter because this Cartan decomposition method is not depends on the simulation time t. And there are some future works. And there are other methods to decompose K, the recursive Cartan decomposition, because if we find some Cartan subalgebra, Lie subalgebra K that should have very big dimension in general cases, so we can decompose K recursively. And that will use some difficult mathematical symmetric properties. So I will don't gonna explain about that. And there are another method about the root space decomposition. This is there are concept of the root in Lie algebra, which is a very important concept in Lie algebra. And so, thank you. This is my presentation. If you have any questions, feel free to contact. Thank you.
Yeah, I have a quick question about Cartan decomposition. How is it related to the Cartan generators in the Lie algebra?
Cartan generator to the algebra.
Yeah, so Cartan generators are the largest set of commuting Hermitian generators, which is
Yes, yes.
diagonalizable.
Yeah.
How is that related to Cartan decomposition?
Because if we have a large space about generated by Hamiltonian, like Heisenberg model, and that we should use many variables in the decomposed vector large K, because large K is the all product of the all bases in the Lie subalgebra generated by the Hamiltonian. Did you ask about that or other?
So your model is all about the SU2 symmetry, right? Because we use the Pauli string for Hamiltonian simulations. And
Yes.
SU2 symmetry only has single Cartan decomposition, single Cartan generators. The general SUN group has n-1 Cartan generators, which are simultaneously diagonalizable. So I guess your presentation is only limited to, as far as I'm concerned, only for SU2 symmetry situations. Can you expand it to other higher dimensional systems, which has general SUN symmetry?
I I think there are other dislocation about the risk that kind of symmetries. So this recursive Cartan decomposition method is deeply analyzed some symmetries in the symmetric spaces.
Yeah, because in tensor networks, we can also use symmetries to drastically decrease the computational resource. Like for example, if you have a one-dimensional Hubbard model that has at half filling, the Hubbard model has the so-called particle Hall symmetry. So it has SU2 spin symmetry and SU2 charge symmetry, meaning that not only the number of spins or number of charges considered, but also their quantum numbers is also preserved. So using those properties, we can actually decompose the individual matrix product states into several different subcategories that all contains those kind of symmetries. By further decomposing the individual MPSs by using the symmetric properties, we can even further decrease the computational resources. That's also possible for tensor networks. Actually, we already have a tensor network library that works for general SUN symmetry, like general SUN spin symmetry, SUN orbital, or SUN charge symmetry. And further implying this, we can also perform like much higher dimensional numerical renormalization group in tensor networks. So I'm just wondering whether that's also possible for this Cartan decomposition methods.
I don't know about that. Thank you.
So I have a quick question about basically the general motivation around this subject, I guess. And pardon the loud humming noises. I'm in the lab right now, so so basically the goal of using this decomposition, is it to use a more general mathematical framework to like speed up the simulation of our Hamiltonian, or is there a more physical motivation behind using this decomposition, or is it just simply to just do math faster, I guess?
I think this thesis is about just a trial to overcome the no fast forwarding theorem, because basically many general Hamiltonians have a large GH, so we should consider about the many bases. But if we have some limited bases generated by some Hamiltonian, we can simulate in the fixed depth, doesn't matter about the time t. So I think this is not general method for all Hamiltonians. Only we can use in the that the Hamiltonian that has very few the algebra basis.
Okay, thanks.
Can I ask a quick question as well?
Yes.
So, like, is it if the basis the number of bases is fixed, then the circuit depth is also fixed, but as the Lie algebra basis increases, then that fixed depth also increases. Is that correct?
Yes, the depth is increases, and also we should consider more um uh, uh more more basis and um yes, more variables. Yes.
Right. Thanks.
So I have one last question. How can we categorize the Hamiltonians, like whether they can be decomposed into fixed steps or not? Like, what are the, how can we categorize those Hamiltonians?
Actually, I don't think about that, but this method is very special case because also finding involution is not that easy. Um, uh, Writers just care about some good Hamiltonians that has very easy involutions. But also if we consider other Hamiltonian, we should um, find another involution for that Hamiltonian and found another Lie subalgebra and Cartan subalgebra also.
Okay, thank you.
I have a question, and is the Cartan decomposition expected to be better and generally better, or is there a specific type of Hamiltonian that it is expected to be better?
Yeah, it's about the specific Hamiltonian. There are some conditions. First, the Hamiltonian generates very few has very few Lie algebra bases. And second one is we can find involution of that Hamiltonian. The writer simulated very simple Hamiltonians that has very few bases of Lie algebra and easy involution of this Hamiltonian.
Okay, thank you.
If there's no question anymore, I will end my presentation now. Thank you.
Thank you for presenting, and I think we'll move on to our next presentation now.